The LR circuit with the battery is a pretty straightforward circuit to set up. You've got your resistor, that's the jagged line over here, connected in series with the inductor. You can see we've got the loops here. That's the symbol for the inductor. These two are connected in series and with the battery, which is down here. And in this case, I also have a switch. Don't need a switch, but it's nice because you can turn your circuit on and off. When it's disconnected like this, of course, the circuit is off. You need a closed circuit. This has to be connected in order for the current to flow around. So I want to talk about how this circuit behaves, but it's probably best to begin with how the circuit behaves if there's no inductor. So we're going to take the inductor out, and we're just going to replace it with a wire. So there's no inductor here, it's just a wire. So basically it's just a resistor connected to a battery. And let's look at the first, how the system behaves. And I'm going to leave the switch open for the first 5 seconds. And so for the first 5 seconds, going down here to my graph. Okay. So there's the first 5 seconds, and you can see this is a graph of current versus time. For the first 5 seconds, the switch is open, nothing happens. Then at 5 seconds, I close the switch, and what's going to happen if I only have a resistor connected to the battery is the current is just going to jump up, and I'm going to assume that it jumps up to 9 amps for this example. And this is how it behaves. It jump up to 9 amps essentially instantly, and then it would stay at 9 amps. That's what would happen. If you put the inductor in there, however, the inductor effectively resists any change in current. So the inductor is not going to allow the current to change this drastically. So when you close the switch, instead what happens is it causes the current to increase, but at a slower rate. And so it's going to cause it to do something like this. And we've seen this kind of behavior before, this kind of asymptotic behavior. We saw it with the RC circuit. Recall that for the RC circuit, if we were talking about the charge on the capacitor, for the charge on the capacitor, we had Q max 1 minus e to the negative t over tau. We had that kind of asymptotic behavior. We have the same behavior here, but of course we're talking about the LR circuit. And so for the LR circuit, the behavior is I equals I max 1 minus e to the negative t over tau. So that is how the current behaves in an LR circuit. Now tau is L over R. And remember, if t equals tau, then what we're going to get is I equals I max. This is going to become 1 minus, so if t is tau, then tau over tau is going to cancel. So this is going to be e to the minus 1. So e to the negative 1. And that's approximately equal to e to the minus 1 is 0.368. And so that means in this situation we get approximately 0.632 times I max. So why is this important? I went over this with the RC circuit, but let me go over it here as well. So in our graph, let me make a new graph first. I'm going to delete this. And I want to make a new one because I want it to start at 0. This one started at 5. And I had good reasons for that, but let me make a graph that starts at 0. And so it's going to look like this. Whoops, that's not what I wanted. Let's try it again. There we go. Looks something like that. Okay. And my max current here is 9 amps. That's what I've done. So I want 0.632 of that. Okay, well, 0.632 of I max is about 5.7. Okay, well, so where is 5.7? Well, this is 6. There are 5 tick marks up to get to 9, and it's change of 3. So 3 divided by 5 is 0.6. So 6. So if I go down, this would be 5.4. So 5.7 is essentially right in the middle. So right in the middle is 5.7. And remember, 0.632 times I max is approximately 5.7. I said I max, my I max being 9. So that means I come across like this to there, roughly. And I come down from there, again, roughly. And that right there, just before 15, maybe around 14 seconds, that is tau. So I'm able to read the graph to get an estimate for what tau is. Now, this is not going to give me the exact value for tau, but it gives me a good estimate. And that's important. We want to be able to read graphs. We want to be able to get information out of them. We don't always need absolutely precise information. Sometimes, a good estimate will do just fine. And certainly it is a way for us to check our work. If we are doing some work to calculate tau, we can also look at the graph and make sure that they, roughly speaking, match up.